Okay, so in this lecture, we are sort of trying to introduce the concept of a quotient group. Okay, now if you read any standard textbook on group theory, or if you go for a very basic course on group theory, there is a very standard approach to construct a quotient group. Okay, uh, in this lecture, we are not gonna follow that approach, though I'll give a hint to that approach. But specifically in this lecture, we are obviously going to introduce the concept of quotient group, but we are not going to do that on that standard note. Okay, what we are going to trying to do is we are going to involve the concept of a homomorphism and a very unique structure which is very set theoretic to introduce this concept, and eventually we will also justify why the term quotient is used to denote such a group. Okay. So if I talk about the basic procedure of how a group is structured, the basic procedure is as so we what we do is that we introduce a relation on a group. So if G is a group, this you can find it in any standard textbook or in any basic course on group theory. So if G is a group, we induce a relation on it, a relation on G such that X is equivalent to Y if and only if X minus Y is in, let's say, H. H is a subgroup of G. Clear? I'm using the term equivalent because this relation indeed is an equivalence relation. You can verify it. It's very easy to do so because every element will be equivalent to itself as 0 is inside every subgroup. If x minus y is in H, then minus of x minus y is also in H. Rather, let me follow the standard multiplicative approach. Uh, xy inverse. Okay. Because ordinarily we use the multiplicative notation for groups. So xy inverse is in H. So X is equivalent to itself because so 1 is in H because H is a subgroup. If XY inverse is in H, then by the existence of every inverse of every element, the inverse of XY inverse, which is YX inverse, is also in H, which means Y is also equivalent to X. So what I'm trying to say is that on a very typical note is that X is equivalent to X as 1 is in H. Number 2, if X is equivalent to Y, then that would imply XY inverse is in H, but that would imply XY inverse whole inverse is in H because H is a subgroup, indeed a group itself. So now XY whole inverse, XY inverse whole inverse is YX inverse, but then YX inverse is in H means Y is equivalent to X. So indeed it's symmetric. Later, if X is equivalent to Y and Y is equivalent to some Z, then that would imply XY inverse is in H, YZ inverse is in H. If I compose these two elements by closure, they will be in H as well. It will be in H as well. So Y inverse and Y on by associativity, we can bring it down to identity. So this implies XZ inverse is in H. So this implies X is equivalent to Z. So indeed, this relation is an equivalence relation. Hence, it partitions the group G as a set. What is the structure of each equivalent class? So if I consider the set X, let's say, so this is the set of elements, let's say Y in G, such that, so we have X, Y inverse is in H, right? Or, usually we denote that Y is related to H, Y is related to X, right? So Y X inverse is in H. This is the standard notation we follow, right? But we can write it as the elements Y in G such that Yx inverse is equal to H for some H in capital H. So we can write it as Y belongs to G such that, so this can be written as Y is equals to XH, H is in capital H. And observe that this can be defined as this set, X capital H, because every Y is of this form, right? So this is typically defined as the set of elements of this. I guess it's clear. Okay. These are called the left cosets of H in G. These are called the left cosets of H in G. Clear? Got it? So now, if I consider the collection of all such left cosets, and I denote it as G mod H. So this is the usual notation that this is the collection of all X H, such that X is in uh, X is in G, right? So this is the standard notation, and this set can be structurized as a group by the following notation, that xh dot yh is equals to xyh. Okay. But to denote this operation on G mod H, we need one more additional factor, that H should be a normal subgroup of G. Okay, H must be a normal subgroup of G. Okay, so we are not going to go into details of what a normal subgroup is at this moment, but the main fact is that you immediately can't consider a subgroup. Now see, till we defined this set, there was no need of normality of the subgroup, right? But to define a group structure on this set, you need the subgroup to be normal. Okay. So if a normal subgroup is very typical to define. Okay, let me just define what a normal subgroup is. So H is said to be a normal subgroup of G. This is the notation we use. So this happens if AH is equals to HA for all A in G. Or you can also write it as AHA inverse is equal to H for all A in G. If this happens, then we say H is a normal subgroup of G. Clear? So this additional condition we require to define this operation. We will get into details if needed in some later lecture when we will be defining normal subgroups. So this is the sort of a standard procedure to to talk about the quotient group. Okay. But we are not going to follow this standard approach, because that also needs one additional introduction of normal subgroups. Yet this is very well known approach. That is the main point. We need to go to some different extent to explain this concept. And our main goal is to justify why the term quotient group is there. That will be precise in the approach we will follow. To do that, first let me just formally define what a group homomorphism is once more. Okay. So a definition. I guess I have also discussed this in the previous lecture, but let us do it for completeness. So a map phi from G to H is called a group homomorphism. Nevertheless, G and H are both groups. It's called a group homomorphism. If there are two observations, that is, first is phi is operation preserving. Operation preserving. Now, why I am writing this, you'll get to know. Number two is phi of G1, G2 is a phi of G1 times phi of G2 for all G1, G2 in G. Okay, so what do we mean by it being operation preserving? Is that, see, it's not mandatory that G and H will always have the same operation or the same notation for operation. They can have different notations, or in case different operations as well. G can be a multiplicative group, H can be an additive group. Observe that G1 and G2 are elements from capital G. So G1 and G2 are composed by the operation defined on G. While phi of G1 and phi of G2 are elements in H, right? So they are composed using the operation of H. That is what I mean by operation preserving. For example, if G was a multiplicative group and H was an additive group, then we would write phi of G1, G2, because G1 and G2 are composed by multiplication, right? Is equals to phi of G1. What should be the composition here? It should be plus. Right? This is what I mean to say. Okay. So this is indeed what a group homomorphism is. G and H are groups. What are the very basic properties of a group homomorphism, if I say? One immediate, subgroup which comes out of a group homomorphism, I guess we have also discussed in the previous lecture, I don't exactly remember, is the kernel of a group homomorphism, which is defined as the set of all elements G in capital G, such that G is mapped to the identity element of H under phi. Okay. And one more, we have the image set, which is the set of all elements of the form phi of G, such that G is in capital G. That's it. This is indeed the case. Okay. So my claim that the kernel of phi is a subgroup of G and the image of phi is a subgroup of H. Let's try and prove this. Okay. So if I choose an element from kernel of phi, first of all, the kernel of phi is non-empty because 1 is in the kernel of phi. Right? So this is called the kernel of phi. Kernel of phi, and this is called the image of phi. So 1 belongs to the kernel of phi. It's indeed non-empty. Let us choose elements x and y from kernel of phi. So that means phi of x is 1, phi of y is 1, but phi of y is 1 simply means phi of y inverse is also 1. Right? Because phi of y is 1, we can talk about this in this way. So phi of y inverse is 1 inverse in a way. Right? And phi of y inverse is nothing but, I shouldn't use this term directly. So I mean to say phi of y inverse, correct. So phi of y is 1, phi of y whole inverse is 1, that implies phi of y inverse is 1. So phi of x is 1, phi of y inverse is 1. So what can I say about phi of xy inverse? So it is phi of x times phi of y inverse. Both are 1, so their composition is also 1. So that implies xy inverse is in kernel of phi. Obviously this 1 is in H because phi of x is an element in H. Right? Let's talk about image of phi. This is also pretty easy to observe because first of all the image is non-empty because 1 is an element of H or at least an element of phi of G. Right? So 1 is basically what I'm trying to say is 1 is phi of 1. Right? So it is indeed in the image space. Okay. Clear? Okay. Yeah, let me structureize this as follows. So 1 is in the image space of phi. This indeed also says that identity element is in this. As 1 is nothing but phi of 1. And this element 1 is in G. That's precisely what I'm trying to say. If I choose two elements, say x and y in image of phi. Okay. So if x is an image of phi, then obviously there exists elements g1, g2 in capital G such that phi of g1 is x, phi of g2 is y. What can I say about, so if phi of g2 is y, then that immediately implies phi of g2 inverse is y inverse, right? What you can do is you can just right multiply on both sides by phi of g2 inverse and then you can left multiply on both sides by y inverse, nothing else. So this implies phi of g2 inverse is y inverse. So y inverse is in the form of phi of g2 inverse. So this also immediately means that y inverse is in image of phi. It suffices to show they are closed because inverse we have already shown. What is phi of g1, phi of g2? It is x. That implies phi of g1, g2 is xy. But g1, g2 is an element of capital G. So xy is an element of image of phi. Right? So it's indeed a subgroup. Right? So kernel of phi is a subgroup of G and the image of phi is a subgroup of H. Let's explore some more immediate properties of a group homomorphism. Okay. Properties. Property number 1, that phi of the identity element in G is the identity element in H. Sorry. It's the identity element in H. Phi of G inverse is phi G whole inverse. Now, in a way, I have used this in the above proof. Okay. So it was sort of wrong to do that before introducing it. But for completeness, we will prove it here, obviously. Okay. And number 3 is that phi of g to the power n is phi of g whole to the power n. Obviously for n is in natural numbers. Let's prove these statements one by one. Very easy to prove. See, this can be proved in this way. So I am just using the notation 1. I'm not using the subscript g or h, because you people can obviously understand that when 1 is being used as a pre-image, it's an element in g, and when it is used as a phi of something, then that element is obviously in h, right? So if I use the term phi of 1, it indeed means that this one is the identity element of g. See, phi of 1 and 1, this is equals to phi of 1. Indeed, because 1 composed with 1 gives you 1. But phi of 1 composed with 1, this can be, distributed using homomorphism. This can be written as phi of 1 times phi of 1. Here we have phi of 1. Right? Both are groups, left cancellation holds. So that implies, so this part can be cancelled out using the inverse left, by left multiplying phi of 1 whole inverse. Phi of 1 is 1. Clear? Now using this, we can prove this. How? See, phi of G inverse. Now this obviously holds for all elements G in G. G in capital G. What is phi of G dot G inverse? It's phi of 1, but phi of 1 is proved to be 1. This can be distributed as phi of G dot phi of G inverse is equals to 1. But if I left multiply on both sides by phi of G whole inverse, I get phi of G inverse is equals to phi of G whole inverse. Clear? This is an immediate result from induction. Why? Because what is phi of G squared? Phi of G squared is phi of G dot G, but phi of G dot phi of G is phi of G into phi of G. So it's phi of G whole squared. Rest will immediately proceed by induction. Proceed by induction. You just assume this to hold for any integer n minus 1, and you can show it for n. Okay. If I hold it for hold it to be true for any n minus 1, so I mean to say phi of G to the power n minus 1 is phi of G whole to the power n minus 1. Now if I talk about phi of G to the power n, I can write phi of G to the power n as phi of G to the power n minus 1 dot G, but then I can distribute it using homomorphism. So it's phi of G to the power n minus 1 dot phi of G. Phi of G to the power n minus 1 by the induction hypothesis is phi of G whole to the power n minus 1. Here you have phi of G. So by the law of exponents, this is n. Right. So by induction, it has been proved. These are the most fundamental properties of homomorphism. Okay. Now let us come to the introduction of quotient groups. Okay. You guys know what fibers are? What a fiber is of a given function. So on a general note, let me introduce what a fiber is. So let me just give it as a definition. Let f be a function from a to b. Okay. Let C be a subset of B, and we choose this subset such that its inverse map exists. Okay, that is every element in C is image of some element in E. Okay, you can also, for clarity, you can choose it to be a subset of f of A, whatever. Okay, so we define f inverse C as the set of elements A in capital A such that the image of A is in C. This is the set C. Okay. If C is a singleton set, then f inverse C is f inverse. You can just write it like this, or you can simply write it as, yeah. Let me read it. Let it be written like this one. So these are the set of all those elements which map to B, or which get projected to B, right? So let me just give a pictorial representation. Suppose this is the set A, and say this is the set B. Okay, let us choose, suppose this is a point B1, say this is a point B2. Now, suppose this is the set of elements. Every element gets mapped to B1, so we can think of it being projected to B1 under the map. Similarly, suppose this is the collection of all the elements which get mapped to B2, so we can think of them, the whole set being projected to B2, being shrink down to B2 under the map F. These sets are called the fibers over the elements. Okay, so in this case, this set is called the fiber of F over. So this set eventually becomes the fiber of F over B. And this is the fiber of F over B. Clear? So fibers of a function are basically the set of elements which gets projected to a single point in the codomain set. That's typically what it is. What we do is that we extend this definition to homomorphisms. Okay, so let G and H be groups. Let G and H be groups, and let phi from G to H be a group homomorphism. Okay, be a group homomorphism. The definition of fibers is still the same because G and H are groups, so indeed they are sets. They are non-empty sets, right? Is it clear? Okay. Okay. Now comes the main part, is how we define these fibers. See, any subset you choose of G, the image of that subset is a subset of H, right? Right. Okay. Now, suppose we assign some notations. Let's say. So, for some A in H, denote the fiber of phi over A as, say, chi of A. Okay. So what are we basically doing is, so suppose this is G, suppose this is H. Okay, and say this is the point A. So we have a fiber here of, let this be the fiber. Clear? We denote this set as chi of A. Clear? Okay. Now comes the main fact, is that these fibers are they partition G. These fibers partition G. Why do they do so? Does they, I mean to say that will they intersect at any point? Will they intersect at any point? Suppose there is another point B here, and the fiber of B is, let's say this part. Okay, let's say this is the, okay, let's say this is the yeah, this green part, let's say this is the chi of. Then if you choose an element from the intersection of these 2 points, any element, say x is an element from the intersection of chi A and chi B, then x gets mapped to A as well as to B. This map is no more well defined, right? Then you cannot have a function which does this job. Therefore, obviously they cannot be, intersecting. But if they intersect, they must be identical. Because if x, if x is a point of intersection, then this can't happen. So what is the only option left? Either x must completely map to A, or x must completely map to B. So if the intersecting points have, do so, but these are fibers, right? So every point in the fiber must map to a single point. So if I choose a point from the intersection and I see that it must either completely map to A, or it must either completely map to B, so the whole fiber must do so as well. That means that if chi A intersection chi B is non-empty, then they must be the same. Right? I guess you people can relate this fact with the concept of equivalence classes. Right? In a way that partitions G. Right? I guess that part is completely obvious from here. Okay. Now observe, you choose any partition from G. I should not use any partition from G. So now for any element, any element in H, say A, you have chi A as its fiber, Okay. So if chi A is its fiber, now in a way, bringing A to chi of A is equivalent to saying chi of A is being projected to A by this map, right? That is, bringing A to chi of A is equivalent to saying that under this map phi, we are projecting chi of A back to the point in H. This is in H. Clear? Now observe that if I now start with any fiber, say chi of A is a fiber. Okay, say chi of A is a fiber. Now obviously there is no concept of any property of the function is not needed here. You do not need this to be an onto map or a 1-1 map. We are just talking about the inverses, right? Because in this case we have defined C to be a subset of f of A, but that is not quite necessary. That is not quite necessary. I just said that here for some clarity. This is simply a subset of A. Yeah. C might not contain any the elements of C might not be images to any element in A. In that case, the inverse image will be an empty set simply. Whatever. So if I start with any fiber corresponding to an element in H, I project it down to the element A in H. Now H is a group, right? H is a group, so H has a well-defined group structure. So we start with say two elements, a chi A and chi B, two fibers to be precise. We project them back to H, but we can compose them up. We can compose them up to get AB in H. But when you have an element AB in H, you can compose it. Sorry, you can bring it back to G as a fiber AB. So in a way, using the operation in H, we have defined an operation for the fibers in G, right? Because so if you start with a fiber of A over F, over A of F, you compose it with the fiber over B of F. So what are we actually doing? We are kind of projecting this to A, we are projecting this to B, right? We are projecting this to A, we are projecting this to B, we are composing them up in H because A and B are elements from H. It gives you A dot B, but A dot B can be brought back to the fiber chi of AB. So this can be defined as chi of A dot B. Okay, and this is again a fiber itself. Right? So what are we actually trying to do is that if I construct a set of these fibers of elements over elements in H of the homomorphism phi, then I can define a binary operation in that set, right? By this definition. Okay, so if say chi is the collection of all fibers in in G for H, then we can define a binary operation, in the set in chi, dependent upon the operation in H as well, obviously dependent upon the operation in H. And how is it defined? So chi of A dot chi of B is chi of A dot B, chi of AB in simple language. I guess it's clear. Okay. Now if you start with say three fibers, so you have chi of A, chi of B, chi of C. Suppose you compose them in this way. Okay. So this will eventually be chi of B dot C, chi of BC. So this will in a way become chi of A dot B dot C, right? But A, B and C are elements from H. I can project this to H to the element A dot B dot C. H is a group, the operation in H is associated. So this is same as A dot B dot C, right? So I can again bring it back to the concept of fiber. So this becomes A dot B dot C. But this can be broken down as chi of A dot chi of B dot chi of. Is it clear? Therefore, the operation we have defined is associative as well, right? It's associative as well. Now what is, if you start with 1 in H, so the fiber of 1 is chi of 1. Let's say, what is chi of A dot chi of? So it's in a way we project A to A, chi of A to A, we project chi of 1 to 1 in H, we compose them up, we eventually get 1. I bring it back to G as a fiber, it is chi of A, right? The same will happen if I start with chi of 1 dot chi of A, right? Because if I start with chi of 1 dot chi of A, so I project this to 1, I project this to A, I compose them up, 1 is the identity obviously, so 1 dot A is A, so this is A, so it will bring back this. Therefore, we also have got an identity because 1 is obviously in H, so this fiber is well defined, right? So chi of 1 is the identity as well, right? Okay. I guess you people are now, kind of intuitive behind the concept we are running towards, which is, you know, giving a group structure to the set of all fibers of the elements in H. What can I say about chi A inverse? Okay. Or chi A inverse. Now, chi A inverse is well defined, right? Okay. So, so this is G, this is H. I start with the element A in H. If A is in H, then A inverse is also in H. So if A is in H, you have chi of A. If A inverse is in H, you have chi of A inverse. So what is chi of A dot chi of A inverse? Simply what we do, we project A to A, we project A in chi of A inverse to to A inverse. We compose them up to get 1. But 1 when brought back, it's chi of 1. Chi of 1 was the identity. And I guess you will have already understood it will happen if I place chi A inverse first, right? So therefore for every chi A, we have a chi A inverse such that chi A dot chi A inverse is chi of 1, which is identity, and this is exactly similar to chi A inverse of chi of A. Thus, if I consider the set which contains these fibers, it is indeed a group with this operation, right? Right. Also, each of these fibers, they partition G as well, right? Clear? So therefore this collection, so let me just give a brief thing to what I'm trying to say. So what I'm trying to do here is that I start with a group G and a group H. I give a I give a homomorphism, an arbitrary homomorphism to H, and I see what are the fibers in G with respect to the elements in H. Okay. Okay. I can also start from G as well. I collect those elements which get projected to a single point in H. Okay. Right. Okay. Got it? So I consider the collection of each of these fibers that forms a group. That forms a, got it? This group is essentially called the, the quotient group. Are you getting my point? This group is essentially called the quotient group. So what are we essentially doing? We are sort of, enabling a partition of G. We are choosing each of these partitions, forming a set out of these partitions, and we find out that this set forms a group, and this group operation is indeed coming from the operation in H. Is it clear? Is it clear? So, so observe that. So let me just write it down in statement what I want to say. Observe that multiplication. So I use the term multiplication for denoting an arbitrary group operation. So observe that multiplication of fibers is defined from the multiplication in H. From the multiplication in H. Clear? So by constructing the quotient group, with this multiplication, so it's naturally isomorphic. It's naturally isomorphic to the image of G, under phi. What I'm trying to say, this will become, you can get a hint of what I'm trying to say exactly here if you know the first isomorphism theorem. If you know the first isomorphism theorem. Okay. Let me state the first isomorphism. It's a very simple statement. So it simply says that if phi from G to H is a group homomorphism and K is the kernel of phi, then G mod K is isomorphic to phi of G. And if you know the the standard procedure to construct a quotient group, then I guess you might be able to relate these two statements in a way. Okay. Those who are reading this for the first time, they might not get that clarity, but they will get a more clarity on watching the standard procedure, which we will be eventually covering in after we have introduced the concept of a normal subgroup. But yet of now, please bear with me. Okay, I guess this part is clear. Okay. So now let us end this lecture with a standard example. Okay, example of what is happening. And if you have very little knowledge of what a quotient group really is, if you have worked with examples of a quotient group, then this example might relate you to the standard procedure, to what we have done here. So example, okay, so let us start with G to be Z, and let H be a subgroup of G, or let not H be a subgroup of G. I'm very sorry, we have defined a group homomorphism, right? Because this is a bad habit of the notation H used for denoting subgroups. And let H be the cyclic group generated by X of order n. In a way, we know that any cyclic group of order n is isomorphic to set n, but let it be not introduced at this moment. Clear? Okay. We define a map from Z to H such that, or G to H, such that phi of A is x to the power. Clear? Okay. Is this map injective? Surely not. Surely it's not injective. because what does phi of 2 gets mapped to? Phi of 2 gets mapped to x squared, but phi of n plus 2 also gets mapped, so it gets maps to x to the power n plus 2. It's of order n, right? So it's also x squared. Indeed, uh, it's not 1 1. It's not injective. Is it onto? Is phi onto? If you start with any element in this, so it is of the form x to the power a. But you can surely project a, you can find an element a in Z such that a is mapped to this. It's indeed onto. That's indeed onto. What can I say about choosing any element of the form x to the power a in H and its fiber? Okay. Observe. So let x to the power a be in X. Then what is phi inverse of x to the power a? That is my question. What is phi inverse of x to the power a? So it is the collection of all the elements m in Z such that x to the power, yeah, so m is mapped to x to the power a, right? M is mapped to x to phi of, sorry, I'm mispronouncing the form. So phi of m is equals to x to the power, correct? Yeah, now I've got it. Now phi of m is equals to x to the power a. Clearly phi of m is x to the power m equals to x to the power a. But observe that, by the way we have introduced the fact that why is it not 1 1, you can obviously observe that this can only happen if m is a modulo n, right? So this is the collection of all the elements m in Z such that m is congruent to a modulo n, right? I guess it's clear. So therefore the fibers of phi are simply the residue classes modulo n, are the residue classes modulo n. Clear? Let's give a pictorial representation to this, and then we will be going off from this lecture. So suppose this is your G. G is Z. This is your H. H is the cyclic subgroup. Suppose you choose the point x to the power 0. We consider only three examples, say x to the power 1 and say x to the power n minus 1. What are the elements which will get mapped to x to the power 0? Those are all the elements which are modulo 0, I mean which are congruent to 0 modulo n. What are the elements which are congruent to 0 modulo n? The elements which are divisible by n. What are the elements which are divisible by n? Simply they are 0, plus minus n, plus minus 2n, 2n, and so on. So this set is the fiber over x to the power 0. Getting my point? What are the elements which gets mapped to x to the power 1? Those are the elements which are congruent to 1 modulo n. Those are the elements which are simply of the form plus minus 1, 1 plus 1 plus minus n, sorry, not plus minus 1, 1 plus minus n, 1 plus minus 2n, and so on. Not plus minus 1, I'm very sorry for using that term. So it's 1, let me change the color a bit, one sec. Yeah, this will do. So we start with 1, then 1 plus minus n, 1 plus minus 2n, and so on. So this is the fiber over x to the power 1 under this given map. X to the power n minus 1, those are the elements which are modulo congruent to n minus 1 modulo n. Will minus 1 be there? Obviously minus 1 will be there, right? So yeah, let's do it with this color. Okay, so we have n minus 1 precisely, so n minus 1 is congruent to minus 1 modulo n, whatever. Then we have 1 plus minus, sorry, n minus 1. We can simply do this in terms of minus 1 as well. We can just state it as minus 1 plus minus n, minus 1 plus minus 2n, and so on. So this will get is the fiber over x to the power n. So we are collecting all these sets. Now, if I, represent this as a 0 bar, which are the elements which are congruent to 0 modulo n. If I represent this as 1 bar, if I represent this as say n minus 1 bar, then I get the elements 0 bar, 1 bar until n minus 1 bar. Which I will I get any more elements? I won't. But these elements will obviously cover whatever elements we require. Isn't this exactly the group Z mod nz? How do we form the group Z mod nz? These are the exact elements in the group Z mod nz. That is the reason why we say that Z mod nz is congruent to isomorphic to Zn, because Zn are the elements which we denote as 0 till n minus 1. Those are the elements which are from 0 to n minus 1. The elements from 0 to n minus addition modulo n. But these are the elements, the equivalence classes of 0, equivalence classes of 1 under the equivalence relation of division is exactly the group which denotes Z mod nz. Right? I guess it's clear. So this is one way of also showing that Z mod nz is indeed isomorphic to Zn, because what we have actually showed, the statement which we wrote there, that the quotient group is naturally isomorphic to the image of G under phi. So Z mod nz is indeed the quotient group. It is naturally isomorphic to phi of G, but phi of G, as we shown that phi is onto, so it's indeed Zn, right? Zn in the sense the cyclic group of order. I guess it's clear. One more thing, let's just observe it out from here, that if I choose the element xa from this, then if I denote, so what are we actually doing here? We are denoting the equivalence class. Oh, sorry, I should not use the equivalence class. The class of elements which are congruent to a modulo n, that is the fiber of x to the power a as a bar, right? So what is the operation defined here? If you carefully observe, so x to the power a dot x to the power b is x to the power a plus b. So x to the power a brought to this, x to the power b brought to this will be mapped to, right? So it's x to the power a plus b, so it will map to the class of the fiber over a plus b. This is indeed the operation in Z mod nz, right? One more thing to observe out from here, what is the fiber over 1? It's indeed nz. Every element, you know, sorry, yeah, 1 bar, in a way I should not use the term 1 bar, because we have already classified the fact that it's indeed Zn. I should use 0. Right? So 0 is exactly nz. What is any equivalence class over any element, the fiber over any element in Zn? So it's indeed, if you carefully observe, it's nothing but a plus minus nz. So in a way, if I have an element which is kind of getting mapped to the 0 element in the codomain of the homomorphism, then every other fiber is a translation of that very set, right? We will cover this lecture, this part of this lecture in the in the next part. So meet you guys in the next lecture, and I hope you enjoyed this lecture.